Good morning, FOR 242. It is time to start talking about enhanced forest inventory, or LiDAR-derived forest inventory. In the Brightspace, you'll find a lab area copy.zip, which when unzipped will be able to open like this, and you'll see a whole lot of data sets inside. Before we get started, let's go ahead and change the coordinate system of this project. So under Project, Properties, that opens up. Select NAD 83 UTM Zone 19 North EPSG 26919. Apply. OK. Now we can start adding these data sets. I'm going to just double click and bring them in. And these are 26 meter or 85 foot tall trees and a 50-foot buffer around each one, which displays better if the points are on top of the polygons. You see how that gets hidden. These tall trees might be on our to-do list to go check and see if there's any kind of a hawk nest or an eagle nest in them. And we can also double click on that and bring in the actual outline of the canopy of the tree, which comes from the canopy height model. You only need to add the CHM, not the chm.tiff.over. And let's go ahead and move that down to the bottom. Let's change that to be just an outline, so we want no brush. And then let's go ahead and make that a nice obnoxious green color and a dotted line. Apply. OK. And let's do something similar with this, but not exactly the same. Let's change this simple fill to, let's make this a somewhat obnoxious green, but go ahead and give that some transparency so we can see through it. Apply. OK, so there we go. There's our canopies, or those portions of the canopy that are greater than 26 meters in height. And looking at this closely, I think this is actually two trees close together. So you see higher cells here and here. So there's canopy 1, there's canopy 2. Both of those quite tall. Either of those could host a nest. Zooming out on this canopy height model, we can see the general pattern of this land, where these are ponds, and you can see the buffers around those ponds with taller trees. And we have some mature hardwoods here, some middle-aged, not as tall can be, but taller trees here. Road, road, clear-cut, 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 swampy area. And of course we can change this into a single band pseudo color and select, not that way, but this way, select the magma color ramp. And if we are so inclined, we can change this statistics extent to the updated canvas, as we often do. Apply, OK, and let's expand this a little bit. And as we zoom in, let's see how this changes. Yes, it does. So now we're going from the lowest cell's value here is 3.34 meters, and the highest one is 16.8. So now that's looking familiar. Let's add the elevation model, DEM. And in our processing toolbox, which we can find under View, Panels, Processing Toolbox, if you don't have it, search for the tool Hillshade. If you spell it right, it'll pop up. And there it is. Use the drop down to point it at the elevation model and run. Close. There's a traditional hillshade, but we can also add in the hillshade.tiff, which I've prepared, which is a multi-directional hillshade. I like this one better, so I'm going to right-click and remove that one. OK, and now I can move the elevation model on top, and let's go ahead and set some transparency here. And we'll make that 50% transparent to start. Apply that, but we also need a single band pseudo color with, let's use a spectral color ramp there. And let's do as we've done before, where the statistics extent is the updated canvas. Apply, OK. Now as we zoom in, we get elevation tinted hillshade. This hillshade does come with a black background. If you want to turn that off, let's go ahead and change that. Under transparency and additional no data value, type in 0, apply. Next, let's bring in roads and symbolize those appropriately. Instead of single symbol, we are going to use categorized, and we need to set the value to code. Nothing will happen until you hit classify. F3 is the highest class. Let's make that red. It's already red because I already did this, but let's change that to be a bit thicker. and then F4, next lowest class down. Let's change that to black. Okay. And then F9, that's pure sketchy road. And let's make that black, but we'll make that a dashed line. Okay. Okay. So you see there are only category 4 and category 9 roads within there, but there is a category 3 over here. Only 4 and 9, so either good or very much not good. Now you should still have a connection to the Google Earth imagery down here under XYZ tiles. If not, go ahead and back. I think that was in week 7 that's demonstrated. And go ahead and hit OK through this coordinate system thing. Let's uncheck our elevation model and hill shade. Bring our Google satellite all the way down to the bottom here. And uncheck our canopy height model as well. And now we can see the location of the roads against the air photo. If you look at this category 9 road, you can see the aspen that came up around it, and you can also see the swamp that has filled it up, so that is not going to be passable. So this, I believe, is 2020 imagery, and this canopy height model is from 2015, so you're looking at about 5 years of growth here. So this was pretty low. Not hill shade, canopy height model, thank you. You can see the trees starting to come in here, but they seem to have really filled in the last 5 years. Other spots look very much the same. You can see the trail, this main trail here, and then other small trails either going to it or going to the landing. This is the log landing where the wood was processed. And let's go ahead and uncheck that. Log landing is still fairly open, and you can see some regrowth in here, but this is still in mostly the same orientation as it was. And this is very nice timing for this imagery. We can see the tolerant hardwoods, the shade tolerant hardwoods, the sugar maple and the yellow birch. We can see conifers, spruce and fir, and we can see the aspen all throughout here as this lighter colored green. You can also see aspen around this old road going all the way through here, very common situation. So this fall color imagery is tremendously useful for telling what species are where. So let's uncheck our imagery for now, go back up to our lab folder, and we have lab area, that's just the outline or property bounds, fictitious of course, but here we are. And let's go ahead and make that a no brush with a thick yellow boundary. Show us where we're working. There we go. We also have a slope model, again the .tiff, not the tiff.over. And that is slope in percent, so let's say that we have a machine that does not go over 30% slope, or doesn't like to without tipping over. Let's change the symbology render type into single band pseudo color, and go ahead and classify that. And we want a discrete interpolation. And the mode should be quantile. Change that to be 2 classes. And now we can change this value by double-clicking and just type in 30. And now it's displaying as we wish it to do. And we can change that from a red to a green, for green is good, and change over 30 to be red. Red is bad. Okay. We can also be a little more subtle about it by going and changing that green to be completely transparent. Okay. So now we just have those slopes that are potentially dangerous, which we can overlay on top of our hill shade if we just go ahead and drag that up to the top. So you should be cautious about sending a machine into those areas. And finally, I have a solar radiation model for you, and let's go ahead and change the symbology on that, also to single band pseudo color, and let's check, what do we want to use for that? Let's use a red to gray. And let's go ahead and invert that color ramp, so lower values here, higher values here, apply, OK, uncheck slope, uncheck hill shade. This is the total solar radiation in watt hours. I think over the course of a year, it's been a while since I've run that, but you see how the north slope does not get as much sun. A south slope, on the other hand, gets quite a lot of sun, and especially in winter this can be important for something like a deer yard. So if you had a nice big area of conifer here where the deer have cover, but then have an open slope here where they have some browse, that could be a nice habitat arrangement. So they have cover here, and then they can come eat here where they get free solar heat, and where the snow will melt the soonest. And finally, the Enhanced Forest Inventory, also called Precision Forest Inventory or LiDAR-derived Forest Inventory. This looks like raster cells, but this is in fact a vector layer, meaning polygons. Those polygons are defined by points at each of the four corners and lines connecting those points into the closed feature. This is done so you can easily use the attributes attached to this in the attribute table. Right-click, open attribute table, and we have a whole lot of attributes measured from the LiDAR point cloud, including height top, average height within that 20 by 20 meter cell, base to live crown, basal area, merchantable basal area, quadratic mean diameter of merchantable trees, trees per hectare merchantable. Merchantable meaning big enough to cut and sell, gross total volume, gross merchantable volume, saw log volume, net merchantable volume, piece size in cubic meters, hardwood percent from 0 to 1, hardwood percent merchantable, and basal area in trees greater than a certain size. That size, or size class, expressed in centimeters. We're not going to use that. And then we have shape length, or perimeter, and shape area. Each square is 20 by 20 meters, therefore 80 meters to go all the way around it in perimeter, and 400 square meters. It is important to know that these gross merchantable volumes and saw log volumes are expressed in cubic meters per hectare. So this cell does not have 109.3 cubic meters of saw log volume on it. It has 109.3 cubic meters per hectare and 400 square meters of area. There are 10,000 square meters per hectare, so 10,000 divided by the 400 actual. This is 1/25th of a hectare. We can use our field calculator to make this a little bit more intuitive. So we're going to call this saw log vol, VOL, and the output field type is going to be a decimal number, real. I'm going to click in this box and type in saw log, or start to type in, and then double click on that to finish. And then just a slash to divide. You can also click to add that slash here. Divide by 25, 1/25th. Okay. So now at the end of this attribute table, you have a new field, saw log volume, that shows the actual saw log volume in cubic meters of that cell itself. Now let's see what we can do with this. So close that, see that little, if I move off here, you see that pencil mark there? That says that the editing is turned on. So right click, toggle editing, save the edits. That saves that addition to the attribute table. Now let's see why this is so fast and useful. Right click, properties, and instead of single symbol, let's show graduated and change this value to saw log volume. Classify. Now it will show in 5 categories from 0 to 7.9 cubic meters per cell. Okay. So you can see in the recent clear cuts, no saw log volume, obviously, that was just harvested. In this mature hardwood stand, quite a lot, but how much? Now I'm going to use my Select Features tool, and instead of using this box that I just click, hold, drag, release, I want a polygon. So I'm going to use this drop down here, Select Features by Polygon. Click once to start, click to make a turn or a vertex. Continue around the area you want to work until you're done and right click. That finishes it. With that selection made, I'm going to use this statistics button. Click the big purple sigma there. And now I need to point it at the right data layer, which is the EFI. And then I need to point it at the right value, which is our saw log volume. So I have 193 cells selected, and the total saw log volume of all of those is 1,057 cubic meters. And you can ask your forest measurements professor how to change that from cubic meters into board feet. For right now, let's go ahead and get a little creative with our firewood calculations. You might have noticed that if you look in here in the attribute table, we have our, let's deselect that for right now, we have a saw log and a gross merchantable volume. The saw log is always less than the gross merchantable volume because not all trees are suitable to be saw logs. well, that's called firewood. So if we subtract the sawlog volume, what's left over is going to be firewood. So let's go ahead and make that calculation using our field calculator. And let's do two things at once here. So open parentheses, GMV minus sawlog, close parentheses. Again, divided by 25, so we have the actual volume per cell. Now let's put all of that inside one more set of parentheses, and that we can use to convert from cubic meters into quarts. There are 35.3147 cubic feet per cubic meter, so multiply by 35.3147. And one more conversion needs to happen here, so all of that is going to go in parentheses as well. So all of this, parentheses, 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 gross merchantable volume versus sawlog volume gives the volume of wood that is not usable as sawlog, meaning firewood. Could also be pulp, but for our purposes we'll say firewood. Divided by 25, that converts it from a per hectare basis to a per cell or a per square basis, times 35.3147 puts that into cubic feet. In the great and good state of Maine, we often use the conversion factor of 80 cubic feet per standard cord. So we have this much in cubic feet divided by 80. So now we have the gross merchantable volume minus the sawlog volume, meaning the amount of firewood, divided by 25, making it the amount of actual firewood within that cell, times 35.3147 to get it into cubic feet, divided by 80 to get it into cords. The output field needs a name, cords, and the output field type needs to be real. So cords, real number, this equation, okay. Now we have a new field, cords. So for every one of these cells, say again we're looking at this operation here, and we're wondering if we just cut the firewood, don't touch the saw logs, only cut firewood, what are we going to end up with here? So now we have this down here, cords, we're going to cut 201 cords, or 202 if we round up. If the firewood stumpage value is $20 per cord times 202, we'll say, $4,000 worth of firewood cut out if you're not touching the saw logs and only touching that wood that is not classified as saw log within this metric. Is that going to be perfect? No. Can you take that to the bank? No. All of this is based on the conversion of LiDAR point cloud data, most importantly the height of trees, into predicted values in metrics that we care about like volume. So everything going on here, which includes a lot more than we can see in this canopy height model, gets averaged up into a 20 by 20 meter cell. That is done by taking a lot of 20 by 20 meter square plots, measuring every tree, finding out exactly what the volume in that cell is, and then building a model so when the point cloud sees this, it predicts an outcome. There are hundreds or thousands of those cells feeding that model. But even with all that data feeding it, it is not perfect. Sometimes it's a little bit high, sometimes it's a little bit low, but when tested it's been found to come out pretty well on the average. One more case of the old saying that all models are wrong but some are useful, meaning that every model is an abstraction of reality. But it can sometimes be a very good abstraction that on the average is accurate, and very good and useful. And it is, as we've talked about before, a snapshot in time. This is what it looked like in 2015. Stuff has happened since then. There's been harvest, there's been wind throw, there's been growth. So this is a point of reference. And it's good to have both this canopy height model and this enhanced forest inventory. So you can say, yeah, it looks like we've got a lot of volume here. But looking at this scale, much taller trees in here, shorter trees over here, shorter trees over here. But I can't circle this and ask it how many cords I expect to get if I don't cut the saw logs. And just to review for my forestry students and introduce my non-forestry students, you might use that to improve the overall condition and quality of the stand while giving growing space to your best saw logs. So you're removing firewood so the saw log quality trees have more room to grow. Very common thing to do on a small woodlot. and also a very common prescription in the North Maine woods where you have good quality growing stock. So first you grow the trees up among dense competition, and then you pick the best ones, give them growing space, and let them grow out. So first up, then out. In any case, this isn't silviculture class, so let's get back to the point here. Right-click, zoom to layer. There's our stand, there's our woodlot, again fictitious of course, but real data. So for the assignment, let's go ahead and demonstrate. Click upon our EFI, click upon our select location. Click, 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 right-click to end. There's our area of interest. Under Vector, Geoprocessing Tools, Dissolve, EFI, check Selected Features Only, and I can create a temporary layer, or I can give this a place to land by saving it to a file. I prefer not to. You may prefer to do so. Go ahead if you do. Run. Close. Now we have the operational bounds proposed, and let's go ahead and make that a simple fill without any fill color at all, so I can change that opacity to 0% or change that to a no brush, and let's go ahead and make that orange and a bit thicker. Okay. This selection is still made, and I can go to EFI and see that I have 181 cells selected with 215 cords of non-sawlog firewood to come out. Go ahead and write that down. That's 215 cords. Now uncheck the EFI. We don't need that for now. And let's also uncheck canopy height model. And I want to see hillshade and elevation. And let's move this down a little bit so that we can have slope on top, and I also want to see the potentially dangerous slopes. So let's go ahead and zoom in here so we can see the roads, we can see the potentially dangerous slopes, and we can see the terrain with elevation. You remember how to make a map from before, so just like we did for our standard forestry stand type map, use that as a guide for all the information, north arrow, the legend, the title, all of that. One like this with elevation and slope. One where you have no elevation, no hillshade, keep the slope, and throw on the air photo. So map number 2 where we have the proposed area of operation and we have the potentially dangerous slopes with the most recent Google satellite air photo. And you might as well check on your tall trees and their buffers. On both of these maps, show the roads, show the property bounds, show the proposed operational bounds, and the total number of cords expected to be harvested if you are only removing the non-sawlog volume, which is what we've done here, 215 cords. And make sure that every layer on this map either has a legend entry showing exactly what it is, or a label making it clear on the map what the feature is. So this could be labeled steep slope, then we could assume that all these other red spots are also steep slopes, or you could have a legend entry showing that red is slopes over 30%. Likewise for all the other layers, so anybody picking up this map should know exactly what they're looking at. What's that dot? That dot is a tree that's greater than 85 feet in height, and that is potentially a nesting site for a hawk or an eagle or something. What is the line around it? That is a 50-foot buffer around those trees, or the points representing them. This yellow line is a property bound, this orange line is a proposed operational boundary. And that is very much the daily work with LiDAR-derived forest inventory.